In this session, I'm going to discuss on k-nearest neighbors. So I'm going to build a k-nearest neighbors model, and let's do the prediction for our output class. So let's take this. So k-nearest neighbors with cross validation. So you have been given a classified data set from a company. They have hidden the feature column names, but have given you the data and the target classes. So we'll try to use k-nearest neighbor to create a model that directly predicts a class for a new data point based off the feature. Based off the feature. So here is the classified data set we have. So first, let me show you. So these are the data points. So these are the features that they have presented with us, and this is the target variable. So we are going to predict the target class for our test data, and also we are going to take account of what is the accuracy of our training and testing data. Okay. So first, let's import basic libraries. We want NumPy, import NumPy as NP. So we need pandas, import pandas as PD, import matplotlib dot pyplot as PLT, and import cborn as SMS. So we need these basic packages. NumPy is for numerical Python, pandas is for working with data frames, matplot is used for 2D data visualization, and higher data visualization which cannot be performed on matplotlib is performed on cborn, which is built on top of matplotlib. Okay. So let's get the data. Set index column is equal to 0 to use the first column as index. So if you see the classified data, you have this 0, 1, 2, 3, 4. So this is our index column. So let's take that as our index column. Okay. So let's call our data frame df1 is equal to pd dot read underscore csv of. So what's our path? So file path, let me copy the file path over here. File path is classified data. Classified data. Okay. Classified data, right? Classified data. Okay. Okay. And also we need to set index. So let's take account of parameters that are present. So read CSV. So index column is by default, index column is none. So we have to pass index column for this. Index column integer. So we are going to pass index column as the zeroth column. Zeroth column is our index column. Index column is equal to 0. So we print the data frame 1. So yes, this is our data frame. So these are the independent variables that we have, and this is the dependent variable. So k-nearest neighbors, what will happen is the test class, when you take the test class, so if you want to know the unknown point data class, so whichever value of k majority class we have for that value of k, so majority of class that lies around that point will be considered is that particular class. Okay. So you have been given a classified data set from a company. Okay, this is the classified data. They have hidden the feature column names. So these are the feature column names that they have hidden. Okay, so they don't want you to know the column names because there can be a biasness that can be lead to some wrong results. Okay, that's why we don't need any bias towards particular features. That's why they have hidden the features. So they have hidden the feature column names, but have given you data and the target class. So we have a data and target class. We'll try to use KNN to create a model that directly predicts a class for a new data point. So let's say you have a new data point and you have these many values for that. So you want to find the target class is 0 or 1. So your model is going to predict that based on the nearest neighbors and majority of classes of the nearest neighbors. Okay. So new data point based on the features. Okay. So we have our data frame. So now let me print df.head over here, df1.head. So let's not print it over here instead. So we have our data frame ahead. So now what you have to do is that you have to standardize the variables. Okay, so in KNN we have already learned that because the KNN classifier predicts the class of a given test observation by identifying observations that are near to it. So what we had discussed in KNN model is so based on the nearest observations, right? So this nearest observation, where KNN model is going to predict the data point of class of the unknown data point. So because the KNN classifier predicts the class of a given test observation by identifying the observations that are related to it, the scale of the variable matters. Okay, so the scale of the variable matters. You want all the variables to be present in the same scale so that it is easy to identify the unknown data point. Otherwise, what happens is that any variables that are on large scale will have a much larger effect on the distance. Okay. So when we are trying to find the distance between the unknown point and the data points around it, so any variable that are on large scale will have much larger effect on the distance between the observations and hence on the KNN classifier as well than the variables that are on a small scale. So let's do the standard scalar. So we know for standard scalar from a scalar that processing scalar dot pre-processing we import standard scalar. So we import standard scalar from scalar dot pre-processing. Let's run this. Okay, no module scalar pre-processing pre-process. Okay, this is it. So okay, we have our standard scalar. So now what you have to do is that let's instantiate this standard scalar to scalar variable. Scalar is equal to standard scalar. Okay, so we have instantiated the standard scalar. Now what you have to do is that now let's take a new data frame df. So df is equal to df1 dot drop of so what so we want to drop this target class. Okay, so since this is a dependent variable, so we are dropping this target class and we are assigning to a data frame called df. Okay, and we have to mention that the target class. Okay, so this is target, so everything is in capital. And we also need to mention axis. Okay, so by default it will say axis is equal to 0, and we want the axis 1 is equal to 1, that is the column needs to be dropped out. So we will pass axis is equal to 1. So let's run this code. Okay, so now let's check over here the df data frame. Okay, df dot head, let's check. Okay, so this is the head. So now we have deleted the target class from our data frame. Okay, so df new data frame. So now what you want to do is that now you have to do the standard scalar, right? So first what we will do, so first scalar we have initiated standard scalar to scale. So scalar dot of, so we have to pass data frame over here. So scalar dot fit of data frame. So this is a data frame, right? So you want this to be converted into a scale where all the variables range are in the same scale. Okay. So we can do fit transform also as well over here. So scalar dot fit, this fit will give you mean and standard deviation. And once you get the mean and standard deviation, you can uh, you can scale it down. So we will do the scaling down of these features. Scaled features, let me consider as a variable. So scaled features is equal to scalar. Now we have our scalar dot fit gives mean and standard deviation. Now we will do the transform. Transform will give the Z score. Okay, so all the values of this data frame lies in the Z score. Okay, scale features give and the range of Z score. So now we have array kind of thing that is present. So let me print this scaled features. So you can see, right? So we have an array over here now. Okay. So now we have to create a data frame for this array. So how we will do that? So we'll pass it as data frame. Let's call this data frame as data frame. So pd dot data frame of. So I will pass scale features comma. So what are the columns? Columns is equal to, so we'll take the columns of this data frame. Okay, so we have our data frame, so which is our data frame, this df1. So df1 data frame columns will take df1 dot columns. So from where to where we want, from till -1. We don't want the target class to be defined present in our the nuclei scaled data set data frame. So we have taken till -1. Okay. So now let's print data frame underscore feed, data frame underscore feed dot head. So you got now the new data frame where all the values, all the features are in the same scale. Okay. So all the features lies in the same scale. So there won't be any biasness towards there won't be any biasness from independent variables to the dependent variables. So since all the values lie in the same scale. So now let's plot a pair plot. So C1 we have pair plot is pair plot. So C1 we have a function called pair plot. So let's plot that. Inside this we will pass data frame df1, and also you have to pass the hue. Okay, on which, so pair plot you want to draw on which variable. Let me pass it data frame and check what will be the answer we get. Okay, so you need to wait for some time to run this code. So this is how the pair plot looks like. So we have both target classes over here, like target class where it is equal to 0 and 1. So for that, we need to take hue is equal to target class, because what will hue does is, so let's check what will hue does. Okay. So in hue, it will differentiate. Okay. Hue will differentiate between target class 0 and target class 1. So name of the variable in data to map plot aspects to different colors. Okay. So it will color in different colors for different classes. Okay, so we'll pass it as a target class. So now when we run the code, you will see it. The target class 0 and target class 1 will be clearly visible, and you could see how the unknown point can be predicted using the features that we have. Okay, so if you have got the all the features data like WTT, PTI, EQM till HQU till NXJ, we'll be able to predict the target class based on these many values. So let's see what kind of plot we get. So it will take some time. So before this gets, so okay, so you could see like right now target class is differentiated between zero target class and target class one. So we have classified based on hue where target class. So here orange represents target class one. So you can see in the right over side over here. So and zero represents target class zero. So depending on all these variables, okay, so depending on all these points for each of the features that we have, the target class will be predicted as 1 as 0. Okay, so now let's do the splitting. Okay, so let's split. So from SQL1 for model selection, let's import train test split. Okay, so let's run this code. So let's take x test, xtrain, xtrain, xtest, y train, y test. is equal to train test split of, so you need to pass the data, that scaled features you have scaled, right? So scaled features you have values. So pass scaled features because you need to pass it in the form of array over here. So I'm passing scaled features since it is already in the form of array. So we have converted into data frame in the next coding line over here, but we want this array format. So we have scale features. Now we want the target class, right? So we want df1 of target class. Okay, so df1 target class. So we have taken a target class, and also we want to pass test size. Test size, let me call it as 0.3, that is 30% of the data is considered for test size. And random state, let me call it as random state is equal to some, okay, 30 or 40, whatever. So let me run this code. Okay. So now using KNN. So now we will build our KNN model. Okay. So till now we have done train test splitting and all. So now we will build our KNN model. So remember that we are trying to come up with a model to predict whether someone will target class Z class or not. Okay. We'll start with k is equal to 3. So let's import k neighbor classifier. So that first we need to take from sklearn dot neighbors import k neighbors classifier. Okay, that's fine. So now let's instantiate k neighbors classifier into KNN. KNN is equal to k neighbors classifier. So we have instantiated KNN, K neighbors classifier. Now let's fit KNN dot. So actually here you need to pass number of neighbors. So we have number of neighbors by default as 5. Let me pass it as number of neighbors is equal to 3. Okay, for now. So now let me train the model. Let the model memorize the extend and ytrain data. Extend comma ytrain. Let me pass extend and ytrain. So the model will, let's train the model. It's like just the model is going to memorize. So we have done that. So now it's the prediction part. So PRD prediction is equal to KNN dot predict. So predict on our X test is okay. Now we pass X test and we'll get the prediction. So we have our prediction data over here. Now predictions and evaluation. So let's evaluate our KNN model. So what we will do from sklearn dot metrics import classification report, a confusion matrix. And also we went from sklearn dot model selection, from sklearn dot model selection. So let's import. So what we want to import is that cross validation score. So we need this cross validation score as well. So this is going to give the best set of training data set and testing data set. Okay. So first let's do the confusion matrix. Okay. So print confusion matrix of, so we have to pass prediction and y test, comma prediction. So let's see the confusion matrix. Okay, so these are the values that we get. So true negative is 130 and true positive is 148. And since this is the actual values and this is predicted, this is true positive and this comes out to be what this is predicted, right? So these are actual predicted. Predicted is positive means this is false positive and this is false negative. Okay, so now let's print the classification. The classification of, so we want classification report for Y test and Y prediction. Y test, Y pre, so prediction data PRE. So we have our classification report. So you could see the precision score for test class 0 is 94% and for test class 1 is 91%. Okay, so we can improve this value still. And recall score is 90% and then for test class 1 it's 95%. So we still can improve this value. So let's choose the best K value. Okay. So how we will choose the best K value? So let's go ahead and use the elbow method to pick a good value. So we for picking a good K value, so we will use elbow method. So first, what is, let's see the accuracy rate. Accuracy rate is equal to, so let's keep it in a form of list. So I range of range of 40. So I'm saying that my K value lies between 1 and 40. Now let me instantiate K neighbor classifier again. K classifier of neighbors, 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 HBORS, and n neighbors. Okay, n underscore neighbors. N neighbors is equal to, let me pass it as I. Okay. Now, so we want the score. Okay. So this score, so we pass cross validation score. So what happens in this cross validation score? You have to pass the KNN model over here, and then you have to pass the data. Okay, the feature, the independent variables data you need to pass. So the independent data is df. We have passed df underscore feed because df underscore feed is a scale data. Let me check. Okay, this is a scale data. So what we are trying to do is that we are trying to find the best k value. So that's why we are trying to pass the model over here. The algorithm KNN, K nearest neighbor classifier algorithm we are passing, and then we are passing the independent variables, and then we are passing the dependent variables df1 of target class. So, and also we have to pass the cross validation K fold. So how many fold we want? We want 10 fold. So what will happen is that this is going to keep on it is going to give the, yeah, so let me tell you what CV does. So cross validation K-fold, CV is cross validation. So what will happen is that we have already seen. So we will have 10 folds. So yeah, 9 folds, 9 will be taken as training, and 10th will be taken as testing in our first fold. Similarly, 8 will be taken as training, and 8, 9, 10 will 8 and 10 till 1 to 8 and 10 will be taken as training, and 9 will be taken as testing. So this process will for complete for whole the data set that are present over in our data set. So whole data set will be used for, so whole data set folds will be 10 folds will be used for training as well as testing, and then you will get a score for each of the folds. Okay, so each of the training and testing, when you do when you do the cross validation for each of the 10 folds, you will get a score for each of them, and then you have to take the average score of that. And after that, so when you take the accuracy rate, so just append that average score on accuracy rate dot append of score dot, so you take the mean value from this score. Okay, for from this score. So let me tell you once again. So once you pass cross validation score over here, then you will pass the more algorithm, the KNN algorithm. Then you have to pass the independent variables and dependent variables, and we will have cross validation K fold. So total we will have CV 10 folds. Okay. So let's see. Cross validation generator or iterable determines the cross validation splitting strategy. So cross validation 10 means so we'll have k one fold will be used for testing data and 10 k minus one fold will be used for training data. So similarly, this will happen for all the folds so that all will be used for training as well as testing, and the score of each of them will be stored in this score, and we are going to take the mean value of that score and then we are going to append it on accuracy rate. Okay. Similarly, you can also find the error rate as well. What you have to do is that for finding error rate, take this code, you take error rate instead here, error rate, and you have passed k nearest neighbor classifier I. Okay, this is fine. Then error rate is equal to error. Error rate is nothing but so error rate you have to pass over here. Error rate dot append. So here score dot mean, right? So you have to pass one minus score dot mean. So this will give you the error rate. Okay. So now what you have to do? So so now let's do the plotting. So figure figure of fixed size is equal to give it as 10 comma 6 and let me dot plt dot plot of so x will be in the range of 1 comma 15, which is our KNN value x. So x is our KNN value, lies between 1 comma 40, and y variable will be what? Y variable will be accuracy rate. Okay, we pass accuracy rate, and let's take the PLT dot title of let's call accuracy rate versus K value. Okay. So now let's dot plt dot x label. Let's give it as x label is uh, x label will be a k value and plt dot y label will be it is y label accuracy rate. So now let's do the printing. So we can actually make sure that there are some dots over here. So let's mark those. So inside PLC dot plot, inside this PLT dot plot, and pass color, the color is equal to red. Let me pass it as red or blue. Let it be blue. So it's blue. Let me pass it as blue or red. Let me pass it as. Okay. And now we can pass other arguments as well. So color we have passed. So now what we want to pass is let me pass the line style. Line style. Stay by so line style is the dashed line. Dashed line on and also marker. So wherever the points are there over here for each of the k value, so we'll have marker is equal, let's say O, okay, O, and marker face color also we can define. So marker face color is let me call it as blue, okay, and let me print this. So let's increase this marker size as well. So marker size, let me increase it to 10. Okay, so you could see. So from this figure, we can see the accuracy rate is higher over here, and it should be stable. Okay, so you can take k value to be 15, or you can take k value to be 20 because here also it's stable. 17, 18, 18, 19, 20 it's stable. Okay, so you can take k value to be 20, or you can take k value to be 20, 25, 27, 27, somewhat like that value. So now let me take some k value. Here we can see that after around k greater than 20, the error rate just tends to hover around zero point 0.6. Okay, so you can see, right, the k value after 20 it hovers around zero point 0.5, 0.06 and 0.05. Okay, it's not 0.06 over here, it's between 0.05. So from here to here it's hovering. There is not much stability also. Let's retrain the model with that and check the classification report. So now what we can do is that, so let's pass first, let's pass number of neighbors as 3. Also in the accuracy, after around k is greater than 20, the accuracy is almost constant. Okay, almost. I mean, it's after k greater than 17. I guess almost constant over here. So let me take once again KNN. So instantiate k neighbors classifier. So k neighbors classifier of n neighbors n is equal to, so what value can I give? We can pass 3 again. So we have already used 3, right? So let me pass 3. And so let me do the fitting part. So let me change the model KNN.fit of. So let me pass X train, comma, Y train. So now let's do the prediction. Prediction is equal to KNN dot fit of X test. So now let's print confusion matrix. So we are doing the same process again and again. So confusion matrix for uh, Y test and prediction. Okay. And also let's me build a classification report for this as well. Classification report of Y test, comma Y prediction. So prediction. Okay. So let me print this. So we had got the same set of answers previously as well. So it won't change like that. So for k number of neighbors classifier, so let's do the plotting as well. So let me see the area under the curve. Okay. So area under the curve will give you the best analysis of what's the true positive rate area. Okay. So for that, from SQL dot, so from SQL, let's import metrics. So now here, so prediction probability, predictions, prob. So actually, this is not a function, predictions, prob. Let me call this variable as prediction program. Take the a model or the algorithm, the trained algorithm over here, that is a model. KNN dot predict proba. So predict proba of pass X test, and what we have passed. So the first column will be the uh, output. Okay. So for X test, whatever you get the prediction probability, whatever you get the first column, that will be your uh, predictions. Okay. So now let's find out the false positive rate, true positive rate, comma extra, comma. So now matrix dot ROC curve, ROC, ROC curve of. So let's pass X test, comma. So for ROC curve, sorry, actually here for ROC curve you have to pass Y test, comma prediction. Okay. Predictions probability. And also, so we want the area under the curve. Okay, area under the curve is matrix dot AUC of false positive rate, comma, true positive rate. Let's do the plotting PLT dot plot of false positive rate, comma, true positive rate, comma, label. Let me label is equal to F. So I'm having a formatted string. So area under the curve is equal to. So I will pass AUC over here. PLT dot legend of allocation is equal to lower right. Let me run this code. Okay. This is how we get the plot. So our area under the curve is 97% over here. Okay. So now with let's test with k is equal to 20. Okay. So now let's pass k is equal to 20. So you don't have to do anything. Copy this code and just paste it and pass it k is equal to 20. So and just run this code. Okay, we are getting a good result compared to the previous one. So let's see the area under the curve for this one as well. So area under the curve will be, let me run this now. So 99%. So you get a huge true positive rate when you have increased the x number of neighbors. So let me check it for 15 as well. Let me run this and let me see. So 99%. Okay. Still, it's giving good result when you increase the number of neighbors. Okay. Let me give number of neighbors as 10. Still, it is giving 9 good result. So let me take it as 6. Okay, so now it's getting 98%. So this was all about the key nearest neighbors. So let me summarize that thing. So what key nearest neighbors does is that, so if you want to find the class of the unknown quantity, it will find the distance of the unknown quantity from the other data points, and it will first sort them in ascending order, and based on the majority class, it will predict the unknown class as that majority class output. Okay, so whatever the majority class we have, that will be predicted as the unknown class variable value, unknown class value. Okay, so this was all about k-nearest neighbors. Hope you enjoyed the session. Thank you for attending the session. So I will be covering the next concepts the coming session, like support vector machine, k means clustering and all. Stay with me for attending further sessions. Thank you.